Well, hello again. This is part 3 of my videos on the AC induction motor. Last time we calculated the current, or at least we wrote the equations, and what we said we would do at the beginning of this part 3 was to go in and actually plot the currents and do the calculations there. So we wrote expressions for calculating the current IS in the stator, and then the IR in the second mesh here, which is due to interaction between the rotor and the stator. So without wasting any more time, let's go in and let's do that. So let's see here. Go to display. And let's pull up our trusty Python stuff. So let's see, let's pull this up. And let's pull up the one for input currents. Okay. Alright, so this is pretty much a lot of the stuff that we had before. But notice that what we're doing is we got the Zn and everything. We're calculating the stator current, right? So this is the complex current. Then we're going in and using the built-in functions of NumPy and Python to calculate the magnitude in the input current. This is the angle of the input current. This is the real part of the input current. And this is the imaginary part. Then what we did was we went in and we calculated IR, which is the rotor current induced in the stator. And this is just that function that you just saw. Okay. Notice it's a function of IS and these other things here. And then we calculate the real part of this, the magnitude, actually the magnitude of this part and the angle. And here again I did actual speeds for various slips. We printed out the different values, the stator magnitude and angle and real and imaginary, and then the magnitude and angle of the rotor current for these slips. And so what we'll do is we'll plot this for the stator magnitude and angle first, and then we'll do it for the stator real and imaginary, and then we'll do it for the rotor magnitude and the rotor angle. Okay, so we'll do 3 sets of plots here. So let's go in and do this first one here. So run. Okay, so here what we have is the actual current flowing, the magnitude of the current flowing in the stator. Okay, the red is the angle, and here's the actual current. Now notice, and we'll see again, and actually I guess I can pull it up right now. Let me pull it up right now. LTSpice, and let me pull up the other one here. The single phase, each phase is going to have pretty much the same current if it's balanced, or pretty close to the same. And so this is the actual current we're going to see on each one of these lines here, essentially, flowing into one of these. And we're just looking at one phase, but essentially you're going to see that much current. Now, the currents, like the voltages on each one of these, are going to be 120 degrees out of phase. So you won't see the same current all the time, but essentially the net current here and the net current here and net current here are essentially the same, even though they're 120 out of phase. And we'll look at that on here. But first let's go ahead and look at this. So that's a lot of current there, right? This is the one thing we don't have to multiply by 3. Notice that here we're talking about what, about 150 or so. Now I didn't look at the slip values, but this is a pretty high current here, in rush current when you first turn it on. Okay, and the phase angle here is about minus what, 50 something. Now this is interesting. You notice that the current going in is basically has a negative phase angle here. Okay, in this case it is negative because what's happening is that the current is lagging the voltage, which makes sense, right? the current's going to be lagging the voltage because it's appearing as an inductive impedance. So an inductive impedance, voltage leads current, Eli the Iceman, right? And current leads voltage in a capacitive circuit. So anyway, that's a lot of current right there, okay? So that's what we've been told and we know. Now let's go in and let's expand this. Okay, and so here we're at a slip of 0.2, which is the operating range here. Then we notice that we get a current down here, which is what, about 18 amps is the magnitude of the current in the stator for a slip of 0.2. But notice what happens when we have a slip of 0.3. When we have a slip of 0.3, then it goes up to about, what, 26 amps, 25.7 amps. And if we have a slip of 4, then basically it goes up to about 32 amps. So it's going from about 18 up to about 32 amps for just a change in slip. And remember what I said is the slip is determined by the load. So if you have a light load, it's not going to draw as much current as if you have a heavier load. Okay, so a slip of 0.4 corresponds to a load that's heavier than a slip of 0.2. But look how much it increased. It increased from like 18 up to about 32. Of course, that's nowhere near the inrush current or the current when you first started up, but it is quite a bit of difference due to the slip. And so if we were to go up to a slip of 0.6, then you can see that there again, this is going up to around 42 amps or so. The other thing to notice is that the angle of this, okay, and this is minus, and notice that as we're going in and getting closer, moving up slipwise, the actual angle is decreasing, okay? So what's happening is the current is getting closer to being in phase with the voltage. So here, what you notice, it's minus 32 degrees for a slip of 0.2. A slip of 0.3 is gone from a minus 32 to a minus 26. We go up to 0.04, the slip is gone to minus 24, okay? And so, and it looks like it's kind of peaking out somewhere around in here, okay? So anyway, that's interesting. All right, so let's go in and let's plot the other plots. All right, so let's go in and let's comment out this. And let's uncomment this. All right, let's plot this. And so this time we're doing the real part and the imaginary part. Okay. All right. So here we have the real component of the current, and here we have the imaginary component, part of the component. And notice, this is interesting, notice that at a slip of 1, you know, or when it's locked or not moving, then it's mostly a real component here, right? IS. And notice that as you move up, the slip goes down, or you increase the speed and get closer, then the real component starts dropping down, the imaginary part comes up. So let's go in and let's see what's happening here. Okay, so with a slip of 0.2, the real part of the component is what? 15.88. If we go up to a slip of 0.3, the real component is 23. Go up to slip of 4, the real component is like 29. Okay, and so the current is increasing with there, the real component. And of course, the imaginary component is going down. Okay, so that's interesting. Okay, let's go back and let's comment this back out. And uncomment this. And let's plot. Yeah. Okay. And so here what we're plotting is the actual current that's actually producing the output power, IR, the magnitude and the angle. And so here again, notice that IR is pretty high. Now notice this was pretty close to what we saw for the stator current. So there again, when it's locked rotor, the rotor current and stator current are pretty close to the same, and it's following the same kind of pattern. Let's go in and let's expand it. And so here again, what we see is for a slip of 0.2, we've got about 16, so it's a little less, but it's close, 16 amps roughly. As we go up to a slip of 0.3, then we're going up to about 23 amps, and in a slip of 0.4, we're going up to about 30 amps. Okay, and notice that the actual angle here is increasing here as we're going up, as we're decreasing this or increasing the slip. Okay, so there you go. There's the current. Going back to here again, we see that this is showing us that we have indeed a very large current on our locked rotor, which is what we would expect. Okay, quite a bit compared to what we're doing in the operating. So when you start up motors, you got really heavy current. Okay, all right, and unfortunately this heavy current is not producing any power, as we'll see in the next slides. It's basically heating up the motor, right? Hence the need for soft start, right? Okay, anyway, let's close this out, and let's close this out. Actually, let's just minimize this, and I'm gonna minimize this and minimize this, and seem to have a whole bunch of stuff there. I got 2 Python shells. Close that one. Okay, now let's go back in to our GIMP. Alright, and what we want to do now is let's go and we want to look, see, what did we just looked at? We looked at, okay, we looked at the currents. Okay, so we want to look at power now. We've already did the currents. Let's go to power. Okay. And so power. We want to know what the power curve looks like. Okay, now there's a couple of ways you can do the power. One way is to look at complex power, and that's what I'm talking about here. We know what the stator current is, we know what the applied voltage stator is. If we basically go in and take the complex conjugate of the input stator current, multiply it by the applied voltage, then the number that we end up with, the real part is going to be the real power in watts, and the imaginary part is going to be the reactive power in volt amperes reactive. Okay, and so we can actually go in and do this in Python. And here, let's see, what else am I doing? Real power, RSR, okay. So this power here, if we look at this component here, notice that this is going to include power loss in the stator resistance as well as power that's transferred from the stator to the rotor, which is RR over S. Now suppose that we have IS equals, this is a complex quantity, is this angle theta, and VS equals this angle phi. Then I complex conjugate is you just go in and change the sign of the angle there. Okay, and so if we multiply this out, you've got IS and VS equals this times the difference in angles between the two. Okay, so if we go in and just write this all out in complex form, we see that the real part is this and the imaginary part is this, right? And this is just using Euler's formula to expand this here. And notice that if phi minus theta is between pi and 0, then Q is positive, so it's an inductive reactance. If it's between minus pi and 0, then Q is negative, or a capacitive reactance. Okay, and so recall that power factor equals the cosine of the angle between the voltage and the current. Okay, and cosine's an even function, so it doesn't matter if it's negative or not, it's still the same thing. And this, of course, equals the real power over the apparent power. And of course, the apparent power is you just take the voltage and multiply it by the current without regard to any angle. The real part is the apparent power times the cosine of the angle. And so this would be watts over volt amperes is the power factor. Okay, and so we got special cases here where P is acting as a motor. If it's equal to 0, then it's acting as a generator. It'd be minus P, and so on. We're not going to really talk about the generator features here. I thought about doing some plots there, and I could do a plot. Maybe I'll do it later if I got time, but that's another video. Okay, and so here what we got is I'm summarizing the power in the stator. So the power you measure, looking into the terminals of the stator, is going to be the power loss due to the stator resistance, plus the power loss due to the rotor resistance, the reflected resistance, plus the mechanical power going to the shaft. And so if I go in and plug these in, then what I've got is I've got the real power that you see looking in from the stator terminals is going to be IS squared times RS plus IR squared times RR plus IR squared times this thing here, and this is actually power to the shaft, right? Some of this is overcoming resistance and windage and things like that, but essentially this is to rotate the shaft, and this is just losses in the rotor due to resistance in the loops. Okay, so this is the power we see. So if we wanted to know what this was, we could actually go in and calculate the real part, which is easy to do, and subtract these two, and that would give us that power. Okay, so let's go in and let's do some calculations. So let's get out of here, display, and let's go to here. Let's bring this, nope, I don't want to bring that up yet. We'll bring that up in a minute. Okay, and so let's look up here. So we got this, and let's bring up my shell. Okay, and so here we go. This is the output power. So we got a lot of the same stuff here that we've been calculating for the ZN, the ISs, the IRs. Here I've gone in and calculated the power factor. Now I've got two ways of calculating, but I plotted them. They're the same, and which makes sense. This is ISA is the angle of the input current, okay? And so I had this set up to do degrees, so to use cosine in Python and many other languages, you need to be in radians. And so I got degrees to radians of this, and so what I'm doing is actually calculating the cosine of the angle of ISA. Now, notice that the voltage is considered to be a reference of angle 0. So essentially the voltage is angle 0. So essentially what we have here is the power factor is going to be that way. And down here I did it doing a different way, which I'll talk in a minute. But anyway, either one of these ways are valid. Okay, so IR, this is what we calculated last time. PR is the output power of the motor per phase, and so if I want for the whole motor, I'd have to multiply by 3. But anyway, what I'm doing is taking IR magnitude, squaring it, multiplying it by IR times this. So this is the actual power that's being sent out for rotating the motor or the shaft. Okay, and here what I'm saying is RC. Here's another way to do it. I'm saying RC is the conjugate of IS times VS, complex power. And remember, we said that the real part of this is going to be the real power, and the imaginary part is going to be the volt amperes reactive. By just doing this is the easy way to do it. So here I say PSR is the real part of this, the real power input to the stator terminals. PSI is the imaginary power to the stators. And here what I've done is I'm saying, okay, well, I'm looking from the input terminals of the stator. So if I want to know what the actual output power is to turn the motor, then I need to subtract from this the power loss in the stator resistance and the power loss due to the IR square losses in the rotor. Okay, and so that will leave me, I'm correcting it so that this will actually give pretty much the same thing as this here. So here I'm directly calculating the output power to rotate the shaft, and here I'm indirectly doing it. Okay, and so here again, this power factor here, what I'm doing is I'm saying, well, it's PSR, okay, which is the real power, okay, divided by the magnitude here. Okay, so this is to get the another way to get the power factor. And so here's just different speeds, and so here I go in and actually print out the results again. So this first time what I'm going to do is I'm going to look at PSR, right? And so this is real power, stator input power. So this is the power that you're seeing, whatever is hooked, the power supply, the AC mains that's hooked up to the motor. This is the actual power that it's seeing in there, the real part of it. And here what I'm doing is printing out the actual shaft power. Okay, so this is power that's going in, real power that's going in, and so this includes the losses, and this is the power that's actually going in to turn the motor. Okay, so this is PR and this is PSR, the real. Okay, so let's run this. All right, so what I see here is the green here is the real power input. So this is what you see from the terminals, the real power input. This right here is the actual power going in to turn the motor. Okay, the shaft power. Okay, and so notice that a lot of power initially when it's locked, right? Okay, so let's go in and let's expand this. All right, and this looks good. So shaft power here, notice the shaft power here is kind of peaking out somewhere around 0.15, right? So this is maximum power that you can get out of this motor here. Okay, the peak power out. And this right here is the real power that's seen from the stator terminals. Okay, now these are different scales here, so don't get confused and make this is bigger. Let's look at some values here. So at a slip of 0.02, what we see is the shaft power is somewhere around here, around 1800, and the actual power into the stator terminals is somewhere around 2000. So see, these are skewed here. Actually, it's probably better to kind of look over here. So at here, what we have is the actual power. Here, the shaft power is 1874, but the power actually seen, the real part of the power seen from the terminals, from the stator terminals, is this. Okay, so there's more power coming in that's coming out, because you got some of this power is lost in the resistance of the stator and also the resistance of the rotor. Notice also here we have the power factor here. So in this case here we have a power factor of a 0.85, okay, and then we have the stator current here of 18.78, okay. Let's look at a slip 0.3. So in this case here, we obviously have a higher shaft power. It went from here to here, and we have a PSR, which is the actual real part of the power seen looking into the stator terminals of 29, which is greater than that. Power factor's gone up, okay? So for a slip of 0.03, we have a higher power factor of 0.9, and of course so has the stator current. The stator current's gone up to about 25 amps versus what we had at 0.2. And if we go into 0.4, here again we get a higher power factor, and stator current has gone up even more, up to 32, you know, almost double from what it had there, but we're getting more power. Now, if you multiply these powers by 3, that'll be the total power that's available to turn the load, but we're working on a per phase basis here, okay? Alright, so let's close this, and let's comment out, let's comment this out. Uncomment this. Alright, and let's run this. Okay, so in this case here, what am I doing different? Well, I'm looking at stator current, magnitude, and power factor. Okay, and power factor is going from 0 to 1. So a power factor of 1 means that you don't have really any reactive power, and that's a good thing. So let's expand this. So down here, of course, the red is power factor is really low. Of course, we're not operating here. This is a transient condition here. Okay, so let's look at this. If we have 0.02 for the slip, okay, then the power factor here is about 0.85, and notice that we have stator current is what, about 18 amps. We go up to 0.3, then it's going to 0.9, and we got 25 again, and so on. So here it's just, we're just plotting the power factor. We didn't plot it before, but notice the power factor is increasing up, and it looks like the power factor is getting right around 0.5. It's kind of peaking out. But good power factor is good because that means that you have very little reactor power, and so we got like a power factor of 0.91, so that's good. Low power factors are bad because that means you have really large currents, and most of it's reactive power, but it doesn't matter as far as the power company is concerned. That's bad. They need bigger cables and stuff to carry that heavier current. So it looks like 0.2 to 0.4, 0.4 may be even good, or 0.3 gives you a higher power factor. So something maybe to consider, to maybe adjust the load so that you can be operating at a little higher slip. Okay, there we go. All right, so let's go in and let's get out of here. Okay, and let's go back to GIMP here. All right. And so now let's get into the really interesting part here. Let's look at motor torque. Okay, so this is going to be really simple. The mechanical torque, okay, watts to the motor shaft or whatever, equals the torque, or mechanical power equals the torque times the actual shaft rotation. This is your typical equation for rotational dynamics, okay? Power equals torque times speed. Now here, what we're doing is we're saying, well, then torque equals power mechanical over the speed, but we notice that the slip equals this, so we can solve this to the actual motor speed, and we've already used this equation many times in our other programs, okay? So I actually go in and replace that into here, so we have an equation for the torque. The torque equals the mechanical power, which we've already calculated, divided by this. This will give us the actual speed. Now, the mechanical, P mechanical depends on S, can be found by P mechanical equals this, okay? And measuring the transfer here. So these are the two ways to do it. Okay, so let's go in and let's do some plots. All right, so let's get out of here. Let's go back into here. And let's see, I need this. And I need the torque one. All right. So here's the torque one, and notice the torque, pretty much the same stuff. The only thing different here is I've got a torque equation here, okay? So mechanical torque, all right? And notice I did something here. There's a standard formula for actually estimating the line current, okay? And essentially it's this. If you know the horsepower, and you know the voltage line to line, then the line current can be approximated by the horsepower times 746, because it's 746 watts per horsepower, and then you take the line to line voltage, which is in our case is 220, and you multiply it times the square root of 3 times the power factor times the efficiency, okay? And so in addition to our other calculations here, our other plots, actually go through and calculate that. Use this standard calculation for the full load current to see how close it comes to these other calculations, okay? And so let's go through and let's do a plot, okay? So let's go here and let's run it and do some calculations and do our plot. And wow, look at this plot. Okay, so let's look first at the graph here. Okay, wow, so what do we got here? So we got torque here, which is this blue dash line here. Then what we have is we have the mechanical power, which is this red line, and notice that this is peaking out closer to the synchronous speed than the peak torque. So this is the peak torque and this is actual peak power. Okay, and then I have here is the current at the stator, and so you can see here that basically you have a really large current flowing here, around 150 in each one of the stator windings, or stator lines coming in, the three-phase lines. Okay, so that's important there. So let's go in and let's expand this. Okay, now let's do some calculations here. First off, let me go back to here and say something here. Notice I've drawn a horizontal line here. This horizontal line corresponds to the startup torque, okay? So if you have a load and its load torque is greater than this line here, it'll never start because the motor, this is the maximum torque that this motor can produce. And this turns out being, what, somewhere around 25 values for the torque, Newton meters. So if you're going in and you're hooking a load directly to this motor, it better not have a load torque greater than about 25 Newton meters. If it is, it's never going to start. It's just going to sit there, and this current's just going to eventually burn up that motor. Okay. So at the very least, you're going to smell some smoke if something doesn't, if it doesn't shut down. Hopefully, it's not directly hooked to it. It's got some device that's going to shut it down before then. Okay. So that's the importance of that curve right here. This is the maximum torque that this motor can produce per phase. Okay, this is per phase. And you multiply this times 3, and that will give you the maximum torque. Okay, so let's go back. All right, so with the slip of 0.2, what we have is the actual torque that we're operating at. Okay, looks like it's somewhere around, what, 15 Newton meters per phase. And there again, 3 times that would be the total torque. Okay, so if you have a motor whose load torque is less than, it's going to work because it's less than that. Okay. The red one is showing the mechanical power that we're getting out here. Okay. And this is over here, so this is about, what, about 1800 watts. And then the green one is showing the actual current at the stator, okay? And the current at the stator looks like it's somewhere around 18 amps or so, okay? Now, let's move this up to a slip of 3, okay? So in this case here, looking at the torque, we see that this is below the maximum torque per phase. And so if we had a load, we could possibly operate at this value. Okay. It may not operate that quick. It may be kind of slow to start because of that, and you may have some problems there, but it should start. Okay. The current is going up to about, what, 25 amps or so, 26 amps maybe. And the actual power that we're dissipating, or actually generating, is somewhere around here, around 2800 watts. Okay. Now notice what happens if we have a slip of 4. Now we're talking about maybe going a little higher slip because of the power factor, but look what happens if you go to a slip of 0.4. Now the torque here, okay, the torque is basically above this point here. So your load can't possibly do that. Now, you know, I have to go back and qualify what I said. This is assuming that you have a constant torque load. Now, if you had a torque load like a fan that was like quadratic, so it started out low, then you could be operating at a higher speed here. But if you have a constant torque load, like a hoist or something like that, then this is not going to work at a slip of 3 because it'll never get started. Okay, and then here, this is power. So going back to here, back to this one here. So here, if you have a constant torque, then basically load, then basically this is the max you can get, and look like a slip of 0.3 would work. A slip of 0.4 will not work for this. But if you had like a fan whose torque followed like a quadratic, okay, then that would work. That would probably work. So anything that has a quadratic that starts out with a low torque and then increases torque, then it would be operating somewhere along this points here, and it could work. It could work. But a constant torque type load would not work at a slip of 4 according to this model here. Okay? All right. So there you go. Here's the current, the high current at startup, the low mechanical torque. This right here is mechanical power, is practically 0 to, right? Now, don't get caught up by the curves. Even when these curves are different, the zeros aren't necessarily lined up. Okay? So there you go. This is what we were working towards. This was basically the big curves that we wanted to see. And here's the operating range. Okay, time is up. So let's go ahead and shut this down. And what I want to do next is actually go in and look at LTSpice and look at the results there. Okay, see you next time in part 4.